Let's have a look at this problem now. It's a fair bit of kinematics, but there's also some electric fields and forces involved here. We have a small object with mass m and charge q, and it's got an initial speed of 5,000 meters per second. It's projected into a uniform electric field, so right off the bat we know there's going to be a force, between two parallel metal plates with length 26 centimeters. There's an electric field between the plates that points down with magnitude of 800 newtons per coulomb. The object passes on through without hitting the lower plate. After it passes through, then it gets deflected further downward, so it ends up 1.25 centimeters underneath its original path. We're told to ignore gravity and air resistance, and we want to find the charge to mass ratio. What is Q over M? So why don't we have a look at the path here? What happens to this charged particle as it moves? And then we'll think about how we're going to analyze it. I'm going to draw out the path on a copied image of this picture on the next slide. Here's our zoomed in image. Let's see if we can think about that path now. While the charged particle is between the plates of the capacitor, it's going to feel an electric force because F equals Q times E. If there's a force, then there's an acceleration, so it's going to deflect downwards. There'll be a curved path somewhat down. When it leaves the area of the capacitor, there's no more force because we're told to ignore gravity. That means it carries on in a straight line with the same velocity. Okay, I've exaggerated the motion a little bit compared to the previous slide just to make it a little easier to see. So if we think about what happens inside the plates, it deflects down by a distance equals y1. If we think about what happens outside the plates, it deflects down by a distance y2. And then all together, those distances add together to give a distance of d, which we're told is 1.25 centimeters down. So we know how far down it deflects. We know it's comprised of two vertical distances, y1 and y2. And we know that together, y1 plus y2 equals d. We can write down something for y1 and write down something for y2. Then we can put those together and we should be able to find our charge to mass ratio. Let's get started on y1 first. Let's write down a kinematics equation to see if we can find y1. We know that y is equal to, or y1 I suppose we'll say, is equal to v0 y1, so the y component of the initial velocity times time t1, the amount of time it spends in the first region, plus 1/2 times a1, the acceleration in the first region, times t1 squared. Okay, right off the bat, v initial y1 equals 0 because it comes in horizontally. So our first term is gone. Don't have to worry about that guy. Next, A1 is the acceleration in region 1, the 26 centimeter long capacitor. We know that acceleration is force over mass because F equals ma. And we know that force is charge times electric field. The force points down because the electric field points down. So minus QE over M. Our electric field E is 800 newtons per coulomb. To keep things simple, I'm going to drop my units here. If you prefer to keep them in, you certainly may. What is our time t1? Well, let's think about the horizontal motion. We know that the distance it travels x1, 26 centimeters, is the x component of velocity, v initial x for the first region, times t1. So our t1 then is going to be x1 over vox1. 26 centimeters, put that in meters, divided by the velocity, which is 5,000 meters per second. And we get t1 is equal to 5.2 times 10 to the minus 5 seconds. Okay, let's put this together for our y1. We've got 1/2 times minus q over m times 800 times 5.2 times 10 to the minus 5 squared. Run all that through the calculator and what we get is minus 1.0816 times 10 to the minus 6 times Q over M. Q over M is the charge to mass ratio. That's what we're trying to find. Okay, we've got our Y1. Next we'll get our Y2 and then we'll put them together to find our Q over M. Let's use a similar strategy now to find our Y2. y2 equals v0 y2, so our initial component of y velocity when it's in the second region, times t2 plus 1/2 times a2 times t2 squared. Right off the bat, a2 is equal to 0. We're told there's no field outside the capacitor, and we're also told to ignore gravity. That makes this entire term 0. Okay, what next? What is our v0 to y? v0 to y is the y component of velocity when the charge leaves the area of the electric field. So voy2 is equal to voy1 when it starts in the electric field plus the acceleration times time. The acceleration when it's in the field times the time it spends in the field. We're trying to find a final velocity, the velocity when it leaves the capacitor. voy1, that's 0. a1, we found that on the previous slide, that's minus q over m times 800. T1 we also found on the previous slide, 5.2 times 10 to the minus 5 seconds. That gives us a VOY2 of minus 0.0416 times Q over M. Okay, the other thing we have to sort out, what is our T2? How long does it take to travel the 56 centimeters? We know that X2 is VOX, the X component of velocity, in the second region, times T2. The X component of velocity never ever changes because there's no horizontal acceleration. So we'll solve for our T2. It's X2 over VOX2, 56 centimeters, which we put in meters, divided by the velocity in the X direction, 5,000 meters per second. That never changed at all. Gives us 1.12 times 10 to the minus 4 seconds. Okay, let's put these two guys together. Y2 is equal to minus 0.0416 times Q over M times T2, which is 1.12 times 10 to the minus 4 seconds. Multiply those guys to get minus 4.6592 times 10 to the minus 6 Q over M. Okay, we've got our Y1, we've got our Y2, we know our D. Let's find our Q over M. Let's fill in our values now. Y1 is minus 1.0816 times 10 to the minus 6 Q over M. Y2 is 4.6592 times 10 to the minus 6 Q over M. D is 1.25 centimeters. It points down, so it's negative, and then we'll convert to meters. So we can solve for Q over M then, and we get 2,177. Charge over mass means our units are coulombs over kilograms.